Okay, students. So in our previous lectures, we have been completed following topics: phenomena of refraction of light, types of medium, terms related to refraction, laws of refraction, important cases, then apparent depth, both the cases of apparent depth, and total internal reflection. So if you have any kind of doubt, you can ask. Okay. Otherwise, we will start our fourth topic. So we have two more topics from this chapter. Okay, so our next topic is refraction through spherical surface. Okay, so let's see here. So this is a spherical surface, you can see. Okay, so this is the spherical surface. Now let's see the refractive index for the medium. This medium, outside medium, is mu1. Okay, refractive index of this medium is mu1, and this is the object. The object is placed here. This O is the object. Let's say this point as P point. Okay, and refractive index of inside this is mu2. Okay, so this is the spherical surface, and the object is placed in a medium whose refractive index is mu1. Okay, and this refractive index is mu2. Inside this, I can say, if this is the spherical surface of a material glass, so this is the refractive index of glass, you can say. So this mu1 and mu2. Okay, so there is a light ray which comes from object, and let's say incident at this point here, at this point. Okay, so this is an incident ray, and let's draw a normal on this point. Okay, so this is a normal. This is a normal. So this normal will pass through center of curvature of this spherical surface. So this C is denoting the center of curvature of this spherical surface. Okay, and this angle will be angle of incidence. So this I is the angle of incidence. Now this light ray will travel from this mu1 to mu2. Let's say this mu1 is a rarer medium and this mu2 is a denser medium. Obviously the outside is air. Let if I consider that outside is air and inside is this spherical surface is of glass, so this light ray is traveling from rarer medium to denser medium. So when the light ray travels from rarer medium to denser medium, now you all very well understand that it bends. Okay, it is going from rarer medium to denser medium. Okay, so when the light ray travels from rarer medium to denser medium, it bends towards the normal. So this is a normal. So it bends towards a normal like this. So let's say this point. Okay, so this is my refracted ray. Okay, and let's say this point is M. Okay, now if I take a light ray which comes like this, incident at this point, then it in this case this I becomes zero. This I in this case, if a light ray is coming like this and incident at the point P, then angle of incidence will be zero. And because angle of, and you can understand this thing if you watched or you attended the previous classes. So in this case I is equal to zero, so R is equal to zero. This light ray will go straight like this and intersect at this point. Okay, so where the two refracted rays intersect each other, or I can say actually meet or appears to meet, the image will form. So here image will form. Image of this object is formed at this point. Okay, okay. Now this angle is what? This angle is called angle of refraction. Okay, this angle is called angle of refraction. This distance O to the point P. Okay, O to the point P is called object distance, and the object distance we denoted by U. So what is U? U is the object distance from this spherical surface, or I can say from the center of a spherical surface, this center. Okay, this C is the center of curvature. So this is the U. U is a object distance from the spherical surface, and this distance is called radius of curvature. Okay, radius of curvature is what? Radius of curvature is the distance from the this point P to the center of curvature of this spherical surface, and the distance from P to I is called image distance, and this image distance is denoted by V. Okay, so now you can see here O is a object, P is a midpoint of this spherical surface. Okay, C is called center of curvature. I is image. U is the object distance from the spherical surface or from the center of a spherical surface. C, this R is called radius of curvature, and V is the image distance from the spherical surface. Okay, now let's derive a formula for the refraction through spherical surface. And to derive the formula, let's say that this angle is alpha. Okay, this angle is alpha, this angle is beta, and this angle is gamma. Okay, and drop a perpendicular from here to here. This perpendicular, drop this perpendicular, and this point is N. Now, the aperture of this spherical surface is very small, so I can assume that these P, the point P and point N will coincide over each other. Okay, I am considering that the aperture of this spherical surface is very small, and because of that the point P and point N will coincide over each other. Okay, so just remember this condition. Now to derive the formula, first we apply the Snell's law. So I can write by Snell's law. Okay, so by Snell's law, now you all are comfortable in applying the Snell's law. The light ray is going from mu1 to mu2, rarer to denser medium. So I can write mu21, this mu21 is equal to sine I divided by sine R. Okay, so from, and it is also written as mu2 divided by mu1. So I can write mu1 sine I is equal to mu2 sine R. Now these all angles are very small. All angles are very small. Now because all angles are very small, so by the small angle approximation, I can say that if there is sine theta, so it can taken as theta. If there is tan theta, it will taken as theta. Okay, so we apply this small angle approximation here. So from here I can write mu1 I is equal to mu2 r, and this is my first equation. I hope you understand this. Okay, I just apply the Snell's law. Okay, so Snell's law, the light ray is going from 1 to 2, so mu2 1 is equal to mu2 by mu1 and sine I by sine r, and by the small angle approximation I just write mu1 I is equal to mu2 r. Okay, now let's move forward. Now if I take triangle, in triangle this OMC. Okay, in triangle OMC. So in triangle OMC, this angle is alpha. Okay, and this angle from here to here. Okay, this angle is what? 180 minus I. Okay, this angle is 180 minus I. Alpha plus 180 minus I and plus beta is equal to how much? It will be equal to 180 degree. So cancel out this to this, you will get I is equal to alpha plus beta. Done. Now take in triangle. Now I am taking triangle this CMI, in triangle CMI. Okay. So you can see in this triangle, this angle is this one. This angle is 180 minus beta. So I can write R plus 180 minus beta. Okay. Plus gamma. This one is gamma. So gamma is equal to 180. So cancel out this 180 to 180. You will get R is equal to beta minus gamma. Okay. So I get from this, I get the value of I is equal to alpha plus beta, and value of R is equal to beta minus gamma. So put both these values in equation 1. Okay. So from equation 1, from equation 1. So from equation 1 is mu1 I is equal to mu2 R. Okay. So mu1 Now I is how much? I is alpha plus beta. Okay, and there is mu2, and R is what? R is equal to beta minus gamma. Understand? Okay, so I get this equation mu1 alpha plus beta is equal to mu2 beta minus gamma. Let's say this is my second equation. Okay, now let's see this ray diagram again. Now from this ray diagram in triangle, this OMN, this triangle OMN, if I write tan I, or okay, so this is my triangle OMN. So OMN, let's take tan alpha. So tan alpha is perpendicular by base, means MN divided by this ON. And I just mentioned you in the starting that because of the small aperture, I can consider that this N is coincide with P. So I can write this ON as OP. And what is OP? OP is U. Okay, now U is a object distance. So all the distances by the rules of sign conventions, all the distances should be taken from P. Okay, all the distances should be taken from P, and the distances opposite to the direction of incident ray taken as negative. So in this case, this is incident ray, and this incident ray is moving from left to right. Okay, this incident ray, this is the incident ray. So this incident ray is moving from left to right, and this distance u I am taking from right to left, opposite to this direction. Okay, so according to the rule, I am taking this u as negative. So mn divide by minus u. Okay, I hope you understand this thing. According to sign conventions, all the distances should be taken from pole. Okay, this P point, all the distances should be taken from P, and the distance opposite to the direction of incident light ray is taken as negative. So this is minus u, and by the small angle approximation, I can write alpha is equal to mn divided by minus u. Okay, now let's take another triangle. In triangle this MCN, in triangle MCN. So in this triangle MCN, tan beta I can write. So that tan beta is equal to Mn divided by Cn. Okay, Mn divided by Cn. Okay, so Mn, keep Mn as Mn, and this Cn is R, and is R is positive because the distance you will take from P to C. Okay, so this R Mn divided by R, and I can write beta is equal to Mn divided by R. Now let's take another triangle. In triangle, so now I have a triangle this MIN. This triangle MIN. Okay, so in this triangle I can write tan gamma. So this tan gamma is equal to again perpendicular by base. So Mn divided by In. Okay, so this Mn, then this distance is what? V. So this is V. So gamma from here I can write gamma is equal to Mn divided by V. Okay, so by this doing all these things, we get the values of alpha, beta, and gamma. So the values of this alpha, beta, and gamma just put in our equation number 2. Okay. So from equation number 2, mu1, okay, then this alpha is equal to mn divided by minus u, plus beta is equal to mn divided by r, okay, is equal to mu2. Again, beta is equal to mn divided by r, minus this gamma is equal to mn divided by v. Okay, all these values we just get from here: alpha mn by minus u, beta mn by r, and gamma is equal to mn by v. Okay, so let's simplify this. We get we cancel out mn, mn. Okay, so we'll get minus mu1 by u. Okay, plus mu1 divided by r is equal to mu2 divided by r minus mu2 divided by v. Okay, so from this I can write mu2 divided by v minus mu1 divided by u is equal to mu2 minus mu1 divided by r. Okay, so finally we get this relation, and we use this relation whenever we get a problem related to the refraction through spherical surface. Okay, so and just remember that what is mu2, what is mu1. Mu1 is a refractive index of a medium in which incident rays. So mu1, what you take mu1, wherever the incident rays, it is taken as mu1, then other is v2. V is the image distance, u is the object distance, and r is the radius of curvature. Okay, so this is a derivation for a refraction through spherical surface. I hope you understand this. In case any doubt, you can ask. Okay.